Hello everyone. Welcome to the breakout session on getting started with generative AI with AWS DeepComposer. My name is Rahul Suresh and I'm a software development manager at AWS. As part of the AI ML group at AWS, my organization's goal is to make machine learning accessible to all developers. And to achieve this endeavor, we have launched a number of fun and hands-on products such as DeepLens, DeepRacer, and DeepComposer. Prior to joining AWS, I worked as a senior software developer at Amazon Devices, where I helped launch a number of backend products and devices, including EchoLook and CloudCam. In this breakout session, you will get introduced to generative AI in a fun and hands-on way using AWS DeepComposer. AWS DeepComposer gives developers a creative and a hands-on way to get started with machine learning and generative AI. Get hands-on literally with musical keyboard and the latest machine learning techniques designed to expand your machine learning skills. You will first learn about the basics of machine learning and generative AI. After that, we're going to dive deeper into some of the popular generative AI algorithms. And finally, you will learn to create music using these generative AI techniques using the AWS DeepComposer service. First, our mission at AWS is to make machine learning accessible and easy for all developers and scientists. To help with this endeavor, we have created a portfolio of educational devices to help you get hands-on in unique and fun ways with AWS DeepLens, DeepRacer, and DeepComposer. AWS DeepRacer gives developers a fun way to get started with reinforcement learning using a 1:18 scaled-down version of a car. AWS DeepLens is a compute device with a camera that allows you to get started with deep learning and computer vision. And AWS DeepComposer joins this family to teach you generative AI using music generation as a fun use case. Additionally, for more traditional classroom learning, there are a few options as well. We have a range of online and training materials available. We also partner closely with MOOC courses such as Coursera and EDX to bring relevant courses that helps developers to build their machine learning skills. Now, let us learn more about machine learning and generative AI. First, we want to understand what AI is. AI, or artificial intelligence, refers to the broad capability of machines to perform activities using human-like intelligence. Machine learning is a subset of AI in which the machine learns to improve itself without being programmed to do so. It can achieve this by learning the underlying data or interacting with a dynamic environment. Within a machine learning, you have many popular techniques. Supervised, unsupervised, and reinforcement learning are the three popular techniques in machine learning. Supervised learning refers to the machine learning techniques in which every training sample from the dataset has a corresponding label or output value associated with it. As a result, the algorithm learns to predict labels or output values. For example, let us look at a cat-dog detector. We first label, let's say, 1,000 images of cats and 1,000 images of dogs and feed them into a classifier for training. So the model now learns to differentiate between cat and dogs. So when I feed them a new image, they're able to identify the image as a cat or a dog. So this is supervised learning. The next popular category is unsupervised learning, where unlike supervised learning, there are no labels for the training data here. So the algorithm instead tries to learn the pattern that governs the underlying data. K-means, for example, is an example of unsupervised learning, where the algorithm learns to cluster your data into K different clusters. For example, if you look back at the same cat-dog classifier example, now instead of labeling my images as cats and dogs, I just feed 2,000 images of both cats and dogs to the algorithm and ask it to cluster my data into two clusters. So the algorithm would now identify two clusters in which one would mostly be cats, one would mostly be dogs, but it's been able to do this without being explicitly provided with labels. The final main category of machine learning algorithms is reinforcement learning. Reinforcement learning is a technique where the model learns to make decisions through trial and error by taking actions in an environment. Now let's take AWS DeepRacer, for example, which is a tool for you to get hands-on with reinforcement learning. So AWS Deep Racer gives you a car, and the main goal is to ensure that the car remains on track. Now, rather than making predictions like the way cat dog detector did, the model here learns to stay on the road by taking the right actions, such as steering left, steering right, speeding up, or slowing down. Now, another way to look at categorizing machine learning algorithms is to organize them into discriminative and generative techniques. Now, in discriminative techniques, the model learns to classify or detect. For example, it learns to classify between a cat and a dog or detect a face. So when I take a discriminative model like a cat dog detector and provide an image of a cat, the model is able to say like, hey, this is a cat. Now, in contrast to this, generative models are different because rather than classifying, it learns to create brand new data by sampling from the training data distribution. For example, take a look at the generative model that's trained on cat images and has learned to create brand new images of cats. So when the model is asked to generate a new image, it creates a brand new image of the cat based on its learning. Hence, it's a generative model. Generative AI has been regarded as one of the biggest recent advancements in artificial intelligence technology because of its ability to create something new. It opens the door to an entire world of possibilities for humans and computer creativity, with practical applications emerging across industries, from turning sketches into images for accelerated product development to aiding smart home devices to have extended conversations with users. There are different types of generative AI techniques. It is a category of techniques as we saw before. So in this session, we are going to be looking at some of the popular techniques, including GANs, autoregressive algorithms, and transformers, which is one of the state-of-the-art models in generative AI today. Before we jump into the details about how various generative AI techniques work, let us quickly understand how AWS DeepComposer gives developers a creative way to get started with machine learning and generative AI. First, AWS DeepComposer allows you to create your own melodies using the Music Studio. Then, it allows you to make your music more Bach-like using an autoregressive algorithm called ARCNN. It allows you to add accompaniment tracks or instrument tracks to your melody using GANs. It allows you to extend your melodies using transformers. And finally, it lets you edit your compositions using the Edit Melody feature. Now, let us jump deeper into GANs, or Generative Adversarial Networks, and understand how it works. GANs are one of the most popular generative AI technique that's available today that pits two networks against each other to generate new creative content. The best way I've found to explain this is using the metaphor of an orchestra and a conductor. An orchestra doesn't create amazing music the first time they get together. They have a conductor who both judges their output and coaches them to improve. So an orchestra trains, practices, and tries to generate polished music, and then the conductor works with them both as a judge and as a coach. The conductor is both judging the quality of the output, that is, to check if the right notes were played with the right tempo, and also at the same time providing feedback and coaching to the orchestra. So specifically so that they achieve a style that the orchestra conductor knows. So taking this idea of the orchestra and the conductor, let us examine how GANs work with DeepComposer for music creation. The specific use case that we have implemented is to take a single piano track and show how GANs can add accompanying instrument tracks for different genres. First, we represent music as a special type of image called piano rolls, as you can see in the diagram in the slide. As we saw before, GANs, the idea of GANs is there are two networks competing with each other, the generator and the discriminator, that constantly competes to create new and more realistic music. The generator as the name suggests, tries to create new music, or in this case, instrument tracks, accompanying instrument tracks, in the image type format called piano roll. Now, the discriminator, also called as the critique, tries to critique on how realistic the generated music is. Now, using the feedback from the discriminator, the generator tries to improve the music that it has created. Now, with time, the generator gets better at generating the music and is able to fool the discriminator. So periodically, it is also important that the discriminator is retrained using the new generated data so that the discriminator becomes even better as discerning between generated music and real music. Now, let us hear some samples from AWS DeepComposer that shows how GANs work in practice. So first we're going to hear an input melody with plain notes that shows Twinkle Twinkle Little Star, a very common nursery rhyme. Okay, so this was a plain Twinkle Twinkle Little Star. Now we have GANs that has taken this song and created it into a rock genre, adding all the accompanying instrument tracks to it. Now let's try listening to that. Cool. So now we have seen how GANs are used in a fun use case like music generation. Now let us look at some real world applications where GANs are used heavily. The first use case is drug design and discovery. Recall that generative AI techniques such as GANs allow us to create brand new data such as images. So designing new drug molecules to fight viruses is a hard problem. Scientists today are leveraging the capability of GANs to create new drug-like small molecules that targets novel viral proteins. So this could potentially help us with faster drug design and discovery more so than before. Now, creating original art pieces is another fun example where GANs are being used. Humans and AI can now collaborate to create original artwork never seen before. Humans can bring in their unique creative knowledge, while GANs can be used to create brand new art images from a vast corpus of training dataset on which it was trained. All this data from the training dataset may not be known to a single person. So GAN brings in that knowledge. Finally, cancer or tumor detection is another example. This requires a huge dataset that's not often available. Generative models such as GANs can be used to generate synthetic images of cancer or non-cancer data to augment the training dataset and thereby produce more accurate detection. Okay, so now let's move on to the next generative AI technique, which is called autoregressive models. Now, in GANs, as we saw previously, we use GANs to generate out accompaniment tracks to music, and we noticed that all the accompaniment notes were generated at once, in one go. So these models, where all the output is generated as once, are non-autoregressive models. Now, unlike GANs, autoregressive models represent a category of algorithms where the data is generated in a sequential way, such that the new data generated depends on the previous data. Now, compare this with GANs where everything is generated at once. Now, for example, in the sentence generation, my name is John Doe, the generation of the word John Doe depended on the first three words, my name is. So here, the data is generated sequentially. Now, AWS DeepComposer implements a special type of autoregressive algorithm called ARCNN, or Autoregressive Convolutional Neural Network. This algorithm allows us to take in an input melody and add bark-like chords to it or harmonies to it, thereby enhancing and making your music sound better. Now let us look at how this algorithm works. First, like before, the music is represented as in an image type format, special image called piano roll. At every step, we add or remove a single node, and this is called as an edit event. Now, recall that the node that is added or removed would depend on the other nodes that exist in the song, because this is autoregressive, right? So for example, if the music contains out-of-tune notes, the algorithm will learn to remove the node that is out of tune. Now, if the music is missing some notes, on the other hand, the algorithm will learn to add these notes. The key idea is the node that is added or removed at any step depends on the nodes that have been added or removed until now. This is what makes the algorithm autoregressive, because you add or remove nodes through these events in a sequential way. Now, as part of the training process, we first take the music data is represented as piano roll images. We add random notes or remove random notes from the piano roll to provide as inputs, and we let the model know like the real original music data is the output. So as the training proceeds, the model learns to add or remove notes from the song so that it can convert the out-of-tune music into something that more closely resembles the dataset on which it is trained. So now that you've seen how the autoregressive CNN model works, now let us hear to some samples that was produced using DeepComposer. In the first example, we're going to listen to a song that's out of tune and then see how the algorithm can help remove and improve the out of tune notes. So let's hear the input first. Okay, so clearly the input has a lot of out-of-tune notes. Now let's hear the output and see if the algorithm has been able to detect those notes and remove them. Still, there are a few out-of-tune notes, but you can clearly see that the model has identified many of these and proactively improved those. Now, let's hear the second input melody. Okay, so here the input is good, but we want to make it more Bach-like. So let's see how the algorithm adds Bach-like harmonies and chords to the music. Okay, so let's move on to the next algorithm that we're going to talk about today, which is transformers. Transformers are state-of-the-art models in generating sequential data. So we're going to be looking at it in more detail. Sequence-to-sequence models take a sequence of data, such as music or text, as input and create brand new sequences as output. The length of the input and the output sequences can be different. For example, let's walk through this example. So I'm feeding in a bunch of words into RNNs, which are one of the most basic sequential models. So notice that RNNs are one of the most basic networks that work on sequence data. RNN is recurrent in nature, as it performs the same function for every input of data, while the output of the current input depends on the past computation. Notice from the figure that the ingestion of the input sequence so far is happening sequentially. Now, if we walk through the rest of this image, you'd see that the output is being generated sequentially as well. So this is one of the main disadvantages of RNNs, which are one of the first sequential models, where you're not able to parallelize the data as well as some of the newer models. And the second issue you'd notice with some of the older models, such as RNNs and LSTMs, for example, are that they're able to capture near-term dependencies, but are not able to model long-term dependencies well. So newer algorithms like transformers overcome this using mechanisms called attention, which we will see soon. Unlike traditional autoregressive models like RNNs and LSTMs, transformers stand out in their ability to process data in parallel. With the advent of GPU compute power and the ability to perform distributed training, we can now process massive amounts of data with transformers in parallel, thereby allowing them to outperform their predecessors. Famous models today, such as BERT and GPT, are some of the most powerful in natural language processing, are transformer based, and they have been trained on massive amounts of data that was not possible before. And this is primarily because of a concept called attention that allows transformer to pay attention to long-term dependencies that older models, sequential models, could not. Now, notice from this example that I feed in my entire input sequence at once into the network, and it's able to generate the entire output sequence at once. And this is because of the inherent parallel nature of transformers. Transformer is used in AWS DeepComposer to extend a user-provided melody. They can generate long sequences without losing coherence, as we're going to see in the sample right now. Before we go into that, let's understand how the transformer works. First, we take the music and convert music in MIDI format and convert it to a time-ordered sequence of discrete tokens. This is fed into the model so that it learns to predict new notes or new musical events. You can think of musical notes or events as the same way in which text makes up or words make up a sentence. These events make up a musical score. Now, when the transformer model is now provided with a new user-generated output, it is able to extend the song by predicting the future notes based on the training data on which it was trained. So let us now hear a sample music on Bach and hear how it sounds. So unlike other sequence models like RNNs and LSTMs, transformers, as you heard right now, is able to generate thousands of sequences, thereby thousands of sequences of length more than 1,000 tokens, thereby creating long musical scores that was never possible before. Transformers are being widely used across multiple domains today. One of the most commonly used domain is natural language processing. Being one of the most powerful models in sequence processing, it's used in a wide variety of tasks, including conversational AI, such as having a smart conversation with your smart app, or language translation models, translating text from one language to another, or taking big text paragraphs and summarizing them. These are all hard problems, and transformers do it better than their previous sequence models. Transformers are also used to accurately predict stock prices by training it on massive amounts of historical stock data. And finally, transformer techniques today are also being used in areas like genomics to annotate and label interesting parts of the sequences. Now, we've learned how these different generative AI techniques can be used for music generation. Let's get hands-on with AWS DeepComposer. The first demo is going to take you through the console and show you how you can get started with generative AI using AWS DeepComposer. In this presentation so far, you have been introduced to machine learning and generative AI. You have looked at the various generative AI techniques that's popular today, and also how they relate with music creation. Now let us walk through a live demo to understand how you can get started with AWS DeepComposer. The first thing you'd want to do is enter the AWS Management Console homepage and search for the DeepComposer service. This takes me to the AWS DeepComposer homepage. You'd see a Get Started link here. I would highly recommend everyone to use this, especially if this is the first time you're getting started with the service. There is a lot of learning material that sort of guides you through how to use the service, how to create compositions using AWS DeepComposer, as well as training your own model. There is a special learning aspect available today called learning capsules. Learning capsules are small, easy to understand capsules that allow you to dive deep into various topics related to generative AI. I would highly recommend you all to read through this to increase your understanding of generative AI. Let us look at an example. So here's a learning capsule on the generative adversarial networks, or GANs. So you have various sections that allows you to go through, dive deep, and understand how GANs work. Similarly, we also have sections on ARCNNs. We have sections on training your own model with ARCNNs, as well as a history about sequential modeling. Now, we are going to continue adding more learning capsules with time. So now that you have seen how to get started with generative AI with DeepComposer, now let's look at how to create music using all the techniques that you've studied so far. Once you've gone through the learning capsule, the next feature I'd recommend you to test would be Music Studio. Music Studio is one of the key features of AWS DeepComposer, which provides an immersive UX for you to create your own input melodies, use various generative AI techniques to improve your melody, and use visual tools such as the edit melody feature to collaborate with the AI and post-process your melody. Now, the UI that you see here is what currently exists in our console. However, we have recently launched a brand new version of the UI that makes it easier for learners to use. I highly recommend you to try our new UI for the Music Studio. The first thing you'd want to do in order to create AI-inspired music is to bring in your own input track. So you could either use the AWS DeepComposer keyboard or on any other compatible MIDI keyboard to create your melody. You could also import MIDI files in appropriate formats, or the easiest option would be for you to use one of the sample melodies that's already provided to you. Now let's go with a simple nursery rhyme that we all know, which is Twinkle Twinkle Little Star. Let's play this and hear how it sounds. Okay, so now that you have imported the input melody, let's move on to the next step. The next step is for us to use one of the various generative AI techniques available to improve your melody. So recall from the presentation that the ARCNN algorithm takes your melody and adds and removes notes to make your music more Bach-like. So let's go with that. So let's choose the ARCNN, and you have a number of inference parameters as you see, and these parameters directly affects the quality of your output. So I'm going to leave these at default and move to the next stage. So now your model in the backend is actively improving on the melody. So like you notice, there are a number of new notes that weren't present in the melody that's been added. Now I could enhance it again, send it back to the model to enhance further. The more I do, the more it's going to sound like Bach. So let's play and hear how it sounds. Cool. Now, if you're satisfied with the output of ARCNN, you can move on to the next step. Now, congratulations, we have created our first Bach-inspired Twinkle Twinkle Little Star. The next step is to either use one of the other techniques to further enhance your music. For example, you could use GANs to add instrument tracks or transformers to extend your music. So maybe let's go with adding our instrument tracks. So I'm going to choose one of the two models. In this case, let's go with the default one, which is MuseGAN, and let's choose rock as the genre that we're interested in. So now my GAN algorithm is actively trying to add instrument tracks to my Bach-inspired Twinkle Twinkle Little Star. So let's hear how it sounds. Awesome. So we took a simple Twinkle Twinkle Little Star melody, made it sound more Bach-like using ARCNN, and now we have added rock type instruments to it. So you could do a number of various combinations and play with this tool and have fun with learning generative AI. You have now learned how to get started with AWS DeepComposer, and you've also learned how to create music using the various techniques with AWS DeepComposer while also having fun. Your next task is, or your next challenge could be to participate in one of our ongoing Chartbusters challenge. Chartbusters is a global challenge that we organize where developers use AWS DeepComposer to create original compositions and compete in monthly challenges to showcase their machine learning and generative AI skills. The current challenge, called Keep Calm and Model On, is ongoing right now, and I would encourage you all to participate. We have some quotes from our customers that you can read through. Um, uh, Lena, for example, speaks about how she used machine learning to reduce she used AWS DeepComposer to reduce the barrier into machine learning. Similarly, Catherine, who was one of our previous Chartbusters challenge winners as well, speaks about how DeepComposer inspired her to collaborate with AI to create music. Now, in conclusion, we learned about what generative AI and machine learning is. We learned about the various generative AI techniques, and now we learned about how to create music with AWS DeepComposer. We have a special ongoing offer for you where you can purchase AWS DeepComposer at a discounted price using the coupon code shown on the slide. Finally, here are a few links for you if you want to learn more about machine learning at AWS as well as AWS DeepComposer. Contact us via the AWS forums if you have more questions. Thank you again for listening to this breakout session.